This talk is called The Power of Toys. I'm a software engineer at Vouch. We're building a platform for managing digital identities and digital assets. We're actually working with one of the largest global automotive manufacturers in the world to build digital keys so that dealers on a lot or a customer can operate their vehicle or share a key with a friend to operate that vehicle. So I'm a closurist. I do closure. I'm not going to assume that anybody knows anything. This talk is, we're going to talk about some sophisticated things, but we're always going to keep trying to simplify it. But I'm not going to assume that much. Closure is a functional programming language that runs in the Java virtual machine. It interoperates well with the JVM, for short. Basically, one of the biggest innovations it did is that it presented a functional programming language in the JVM with high-performance data structures. That's one of Rich Hickey's big innovations, that up until he showed that you could take Phil Bagwell's data structures and make them immutable and faster, hadn't really been done. It's been ported since then to many other functional programming languages. I've also been the lead developer of ClojureScript for the past 11 years, so I know a lot about software maintenance, and this talk is about software maintenance, right? The amount of time in which you get to do greenfield stuff, even at a startup, it doesn't last very long. Most of your work as an industrial software developer is maintaining this software, trying to improve it without breaking the existing behavior. I've been lucky enough to be able to use functional programming in Anger for the last years, almost entirely in ClojureScript and Clojure. That means I get paid to work with, in the past, I worked at Cognitech. Cognitech was the company that stewarded Clojure. I worked with small companies, big companies, governments, to try to apply all these fancy ideas you read about in books, you see at conferences, and see if they work in the real world. So my journey as a computer programmer, I sort of started with JavaScript in 2005. I did a lot of UI stuff. I ended up working for startups, various companies, and I was at the New York Times doing JavaScript. On the side, I was doing ClojureScript open source, and then started doing Clojure work professionally and starting in 2014. But my trajectory is like the reverse galaxy brain. When I started out, I was like, oh man, I know so much. This is amazing programming, I love it. And 5 years in, it's like, yeah, this is really cool. I know a lot of stuff. I'm learning more stuff. But maybe that initial enthusiasm is waning a little bit. And then 10 years, I'm like, wow, what do I actually know? Do I know anything at all? And now, I'm like, I don't know anything. And that's a bit of a joke. But in many ways, I describe my career as becoming less enamored with very sophisticated things. Whenever I see people talk about really sophisticated things, I'm like, nah, but man, probably doesn't matter. And in fact, this talk is about most of the sophisticated things about functional programming just don't matter. You can actually take textbook examples. Like the very first toy example people talk about, like in the previous talk, was talking about encoding the Enigma machine as a piece of functional state. That's exactly what I'm going to talk about. That looks like a toy example. Why would you ever do that at work? Except I'm going to demonstrate how we proved a property in a deployed system, like something that matters. People need to be able to unlock their cars. I think a lot of times the most important ideas are toy ideas. They're extremely simple ideas, and they can be applied if you think about, okay, I'm not recommending building toy production systems, but there's this toy mentality, and there is a place to use it. And toy, what is that toy, this word, it means something that's not that important, you could throw it away. And in fact, in this talk, I'm going to talk about how we can use these things in a place where it's safe to make a thing that you might throw it away, you might improve it. It's not in the critical path. It's in the path of software maintenance. And I think that's something that people forget. To maintain the software often means testing, feature development, testing around that feature development. But there are things that you can do that I think can be sort of trifling, but yet give you a lot of confidence that the software is working correctly without, again, doing toy things in the code itself. The actual production code. We're going to actually use toys to reason about the production code. And so this is, really I'm talking about toy models. So we're going to take an inspiration from physicists. So physicists say, well, the real world's really complicated. Never going to be able to write this down. You're never going to be able to simulate it. It's not possible. It's impractical. But, you know, what the physicist says is we can remove most of those variables, and I can still give you an extremely good predictive model. You can run this in the real world, and this will be a very accurate prediction. And this is super important. And that's actually the path that we're going to take. We're going to build toy models to make good predictions about what the future behavior of a production system will be. We'll make a toy model of our system in order to predict the full system. And a lot of this is actually inspired. You know, I did, when I was starting out in 2004, 2005, I was really into object-oriented programming. I'm not that much into object-oriented programming, this idea of modeling state with objects. I think that's the idea I don't like. But I definitely think that Alan Kay, when he started off with this Dynabook idea, which eventually led up to Smalltalk, which really changed the course of mainstream programming. Like, object-oriented programming is an important idea. We learned a lot from it. In fact, there's still things we're learning. But setting the object-oriented part aside, this idea that a computer is a tool for thought, and that he would create this little computer that even children could understand, they could use it, they could build little simulations, and that it was going to be more powerful than just like pen and paper equations, variables, right? You could actually build toy systems on a computer, and you could manipulate them. It would be tactile. It would give us a much deeper understanding of the problems. And that is exactly what we're going to do. We're going to look at a hard software engineering problem, and we're going to convert it into a toy simulation that will tell us what's going to happen, again, in the real world. In order to achieve this, we have to have a good modular thing. I actually, before I did this talk, I was like, what are the biggest toys in the world? What are the most successful, best-selling toys? And of course, I was like, you know, it's arguable, but there's probably a couple candidates, but Lego was consistently way up there for 2022, right? It's like, same thing, 2022. The same thing I played with when I was a child is still going. And there's so many of these different things you can do, and it all boiled down to this idea. I believe the patent for the Lego block was done in 1958, and I think all the dimensions were set. You can actually have a Lego set from the 60s and still plug it into new stuff. I mean, you can't say that about software, right? So what is the sort of universal unit of composition? We have to find that, and I'm going to propose that in a bit, and it's related to functional programming. Same for, I mean, that's like, you know, what's the most popular toy in the real world? Legos. It's not surprising that what's really popular in the digital space is basically kind of Legos, right? Because there's this beautiful, simple idea. A block, you can customize the block, you can arrange the blocks, and you can make analogs of the real world. Right? People love doing this. They love using these toys to build toy models. And that's what I'm proposing we do when we're doing software engineering. We want to test it. Three big areas that we're going to talk about are value-oriented programming. We'll break down what I mean by each of these things, including the databases. It depends on what you're doing. This is not a hard requirement, but it definitely made the approaches we took simpler. We actually use functional persistent data structures, including the database. We use something called datomic, which can be treated as a value. We're going to talk a little bit about symbolic representation and evaluators. These are all things this in particular you probably learn about in school. You build an interpreter. And we're going to talk about stateful property-based testing. This is maybe something that people haven't tried. I don't know. Has anybody ever tried like one of these property-based testing libraries? Like, can I get a show of hands? Like, raise your hand if you're trying. Oh, that's great. So you're familiar. So that's good. That's much more than I thought. So I'm going to show, again, you can find a property-based testing library, and you can combine it with these above things and accomplish what I'm talking about. Now, if you haven't heard these, you're thinking like, wow, these are a lot of big words. And we're going to, for each one of these words, they actually are big topics, like things like value-oriented programming. You could talk about the theory of persistent data structures. Symbolic representation, you could talk about DSLs and like compilers and interpreters, all this stuff. Stateful property-based testing is also a big topic. But actually, for the solution that we came up with we only used the simplest version of each of these seemingly complex topics. And I think the big idea, a big takeaway here, is that, you know, as I've gotten more experience, I'm really generally not a fan of abstraction. Not the way that mainstream programmers talk about it. When people talk about abstraction and making something dry, the very first thing you're going to do is like, if it's Java, you're going to make an interface. If it's like Haskell, you're going to make a type class. All these programming languages, they have this quote-unquote abstraction mechanism. But it's really, I find generally speaking, an inappropriate tool because it's a generalization. This thing that people call abstraction is not actually abstraction. It's generalization. You're actually choosing for the person that's going to implement the thing a specification. You're making a specification, and therefore you're subject to all the problems with specifications. Is that your specification's wrong? Tomorrow, some person's going to come to you and say, we need to do this other thing, and it doesn't, right? And you can't evolve that thing because usually you've shipped that interface, and now it's stuck. And what are you going to do? You're going to bump your semantic version and say, okay, your code's broken, but you can spend the next 3 months updating your stuff, right? It's not what I'm talking about. This form of abstraction, I definitely have a low opinion of now, and exists in all programming languages. I'm talking about a much more powerful one, which doesn't involve any programming technology at all. You can use any programming language, which is to take a thing and to make it as simple as possible. Does not matter what programming language you use. You can, in fact, re-implement everything I'm talking about in this talk in your own language. There's nothing that's going to prevent you from doing that. So value-oriented programming. Programming with values. That's just, in the past, people often, when they were trying to market functional programming, they were like, well, maybe value-oriented programming is a better name. Programming with values, and by that, all I mean is functions and values, right? So you have a function plus, you have an immutable value, 1. It's not like you're creating numbers, right? That's not how we think about numbers. We don't instantiate numbers. It's just plus an immutable value, 1, another immutable value, 1, and I get back another immutable value, right? That's it. Functional programming's basic idea is what happens when you apply that to types that are more interesting than numbers, right? Collections. And if you've been doing functional programming, most functional programming languages have these typical data structures, random access, array-like types, hash maps, sets, all those things. You can do it, especially with these high-performance persistent data structures. The cost is not that high. Going back to the previous talk, then the only leap you have to make is like when you open up a book, a textbook on functional programming, it always talks about, okay, here's a little toy example of the state as the argument. And that's all that we're going to do. That's all we're not going to go past the textbook example. We're going to just embrace this as actually it is the best way to do it. And in fact, we're not going to use a toy state. We're actually put everything. We're actually going to encode the entire world into a single value. The entire state of the world into a single value. It doesn't matter how complicated, it doesn't even be super complicated. We're really going to do it, and that's going to allow us to run a very good simulation. Again, so that seems like a big topic. Well, we're going to just adopt the textbook version of this idea, this concept. Then you have this notion of symbolic commands. Again, you could read all about it, but I'm not going to do anything fancy here. We're not doing anything fancy. Our language is going to be the most toy language. You would say, what can you do with it? It looks like a joke. Exactly. We need it to be that simple. It's going to only have like 4 or 5 instructions. There are no arguments to the command names other than the names of the things we're talking about. There will be no arguments. We'll encode no arguments whatsoever. Even though we're trying to tell a service that there's cryptographic material, there's this manufacturing ID number, all of that will be elided. We only have the name of the command, and we have the names of named things in the world. We'll see later how that's important. But in the case that I'm talking about, we want to tell the system we need to share a key. We're not going to pass the arguments that method needs. We're going to say, look inside the state for these things, and you determine what those arguments are going to be. But I know they're in the world, so go find them. So this is a very big simplification. Our language only has 4 or 5 instructions, and they always refer to named things. And there's no programmatic constructs of any kind. So our language, our toy language, will have no looping, no variables, no constructs of any kind. There will be no constructs of any kind, which makes it trivial to implement. It's like reading, in a textbook. Anybody can understand this because it doesn't do anything at all. Okay, and then the topic, which fortunately some of you are familiar with, so I won't spend as much time on this. And the idea is that once we have a toy command language, we can use stateful property-based testing to generate a sequence of in-string commands. The nice thing about property-based testing is we can, over unit testing, and this talk is not about you should stop unit testing. In fact, we gained a lot of value from our approach in the unit testing phase. We only did the generative test stuff a year later, so they can work hand in hand. But the nice thing about property-based testing is that, when you write the unit test, well, maybe your inputs are, you didn't pick the right domain, the size of those inputs, and maybe it's wrong with this kind of input. Maybe the ordering is subtle and that's wrong. And stateful property-based testing, or property-based testing in general, can help with that. And we'll see that applies to the stateful thing as well. The other thing, if you've tried to use property-based testing for testing stateful systems, of course the thing that you immediately hit is the search problem. If you've tried to do this, is that, well, you want to make commands, but you want the commands to be interesting. And it's not the same as being like, I just picked something from the domain of integers, or I need a collection of integers. It's okay what those are. Anything will satisfy. That is not true once you need a logical sequence of events. The search-based problem immediately becomes a problem because you need some way to limit and to make the commands actually be similar to the things you're seeing in production. So we're going to toyify the search problem, and we'll show how that can be done. Okay, so I'm going to kind of go by this quick because people are familiar with property-based testing. But again, the idea is to generate values. It's not just fuzzing, because property-based testing, it uses pseudo-random number generator to get you reproducibility, so you can reproduce the random sequence of values. And it does a thing that is really awesome, which is it does shrinking. So when your test fails, it will do what a human would do, which is to find a minimal test case, right? Customer says, I did these 50 things, and now it broke. And you're like, well, I'm sure it didn't take 50 things, and you spend a couple days trying to get that down to 3 or 4 steps that produces the same result. But property-based testing nicely does the shrinking, and we're going to use this. We can generate 50 commands, and then property-based testing can shrink it to the 2 commands sequence, the 2 commands in a sequence that cause the failure. Okay, so those are the tools, and then let's drive why we want those tools for this particular problem. I can't talk about everything about the platform or the technology, but this will be a quick overview about the nature of the problem we had and how we use those techniques to solve them. So we're in the business of doing identities and assets on the blockchain. How our platform works is that you all have smartphones. All these smartphones, many of them, especially the new ones, have a secure element. It's a processor that you can't just break open. Both Android and Apple allow you to create a private key pair inside the secure element, and then you can submit, a person shows their Face ID, and what we do is we can't actually sign anything until biometrics is provided. You can control the amount of user presence that's needed, but the idea is that we can use the biometric prompt to allow us to sign their message, right? So what we do on our system is when the person enrolls into our platform, we have their public key. And then we know if we get a message, we check the signature, well, their private key was in the secure element and they needed biometrics, because we also generate the SDK, so we ensure that the secure element is used. We know that that message came from this particular user. So what people might want to do, so we're able to have a high degree of confidence that a particular request was made from a specific user from a specific device, but a person wants to share a key. And actually there's hardware in the car, right? In the car that's going to check something. So when you share a key with a person, it makes a request to our backend, and we update what's called a sparse Merkle tree, which is a cryptographic functional data structure. And again, quick explanation about that. But because of the SMT, the vehicle itself can prove that that person who you shared the key with does have access to that car. So very quickly, sparse Merkle trees, we produce an authoritative document saying, yes, this user has access. All it is that you could think of it as a JSON. And when I say authoritative document, it could be any. It's a blob of like facts, like attributes and their values. That's all it is. and then we stick it inside this tree at a particular key. The key has 256 bits. The sparse Merkle tree is 256 levels deep. If I have a 0, I go left. If I have 1, I go right. Once I'm at the bottom, I write the value. And then what we do is we just hash on the way back up. So I hash that authoritative document. At the next level, I combine the hash of the left and right side. At the next level, left and right side, till I get back to the root of the tree. But what this lets you do is that I can send a proof to you. I only need to provide you the authoritative document and the hashes of the things that you don't know, the hashes of the things on the other side, and then the final hash of the root of the tree. You compute the hashes because you have the other side, and because the cryptographic hash of the final one should match, you know there's no way that that document couldn't be in that tree. You don't even know what's in that tree, but I can give you a proof that the one that you have is. And so then the vehicle says, okay, you can operate this vehicle. Okay, but this already should make you think, oh, the SMT is like this functional data structure, and every time somebody gets a new authoritative document, we get a new root. So that means every time somebody does something with our blockchain technology, we get a value. So our blockchain technology is a function. It's a pure function. You make a request, and we always get this new root back. And just to dive into that more detail, so every transaction in the blockchain is recorded. And the reason this is necessary is we run a cluster of nodes, and they have to agree via consensus that they all believe that the same set of transactions has occurred and that the results of those transactions are the same, meaning the value of this SMT root. So you bring up a new node, and how we bring up a new node is we just replay all the transactions, and that node better arrive at the same SMT root hash. And just to do it one more time, to see this diagram, user wants to do something, share a key, gets submitted to the blockchain. It's a signed transaction from that user. We check the signature. Then we submit it to closure code that does all the business logic. The blockchain says, this transaction is happening. You know what to do. I'm going to record it for all time, this blockchain. I know this happened. You do the business logic and then give me the hash. Give me the hash that is associated with this transaction. And that's what our closure code does. The problem, though, for those of you, that haven't tried to do stuff with blockchain, is what happens when a customer wants you to fix something, or they want you to add a feature? Well, imagine a situation where the first version of your code, and the B is the blockchain function, and it takes a transaction. The first version of the code for these 3 transactions produces hashes A, B, and C. Some developer commits new code to a source tree to implement a requested enhancement, and it's actually computing different hashes. We actually hit this. We actually hit this problem, that different hashes are going to get computed, and once that happens, then the nodes can't reach consensus. You bring up a new node, and it will never agree with the other nodes. Huge problem, because then the service stops working. So there's a way around this, a very boring, typical way. There's 2 parts to it. This one's obvious. We use feature flags. We can't remove old code. Just not allowed. So this is like a completely different level of software maintenance. No old code, no old behavior can ever be removed. You can't do it, because the chain always has to produce the same historical hashes. So we use feature flags. Any new branch of functionality has to be behind this feature flag. And the enablement of that feature flag itself has to be a blockchain transaction, right? So what we do is we allow sysadmins, after the new codes have been deployed, to say, okay, now turn on that feature. And that is recorded by the blockchain, and all the nodes say, this is on now, and we can proceed. So they all upgrade at the same time. And then we get, coherence. Still, that sounds like a solution, but when we're writing the code, when we start adding these feature code branches to our code, how do we really know that the old behavior still works? How do we really know that? We can do it, but how do we, as a team, believe, actually, is the old behavior supported? When we implement a feature, the other thing you don't know, because production is always, like you think you know what's going to happen, then you go to production and you really don't. There's all kinds of problems that happen in production that you never see until later. As much testing as you want to do. How can we increase our confidence? For example, we may have to downgrade. Like we implement a feature, but we realize there's a bug or some other problem that's worse than the fix, and we say, okay, you're going to have to submit a transaction to downgrade that feature until we can figure out what's going on. But how can we know that that's possible? We have to know that it's possible to downgrade, right? We implement a feature, we have to know that we can upgrade, and we have to be able to know that we can downgrade. Based off what you've seen in these earlier diagrams, I mean, you can already tell that integration testing for us is a complete nightmare, right? There's custom hardware in the vehicle, there's custom firmware, there's mobile applications, there's web services, there's backends, and then there's like, third-party services. It's just ridiculous, right? It's not that we don't do integration testing. In fact, the customer's doing integration testing all the time. But even spinning up the system locally on my machine and building all the apps, I mean, this is like 45 minutes down the drain to maybe change one line of code. It's not practical. It is not a practical way to test. So about a year ago, we decided, what if only in the blockchain business logic, we implement a toy model of the clients and the assets and all their interactions. So instead of requiring developers to boot up everything, you can just boot up the blockchain part, the part that actually the closure part, and you can basically create scenarios and simulations there. And that will be a lot faster. So basically what we did is we said for each function in the business logic, each method, whatever you want to call it, we made a toy model of everything. So the clients, mobile phones, assets, vehicles, all that stuff. The mobile phones have cryptographic material, all these things. And we made a special toy model function that takes a new parameter. Right? So originally all the methods look like this. They have a name. They take some argument A, B, C, and they return some type Z. Right? It's like that's how it was. But now the toy model always takes a toy model world as the first argument. The first argument is always the entire known state of the world, and it always returns an updated state of the world. So we encode everything in our sort of simulation. We encode everything into the first argument, and we always return everything the next part. Inside there, this is what it looks like. We have a reference to the Datomic DB, which is an immutable database. We have a reference to our custom-written SMT. And then we have all the devices, all the assets, and everything has a name. Each one of these things has a name. Right? So it's actually in one data structure, a toy model of the world. But this is enough to give us Lego blocks, right? Because the first argument is always the world, and the return value is always the world, you can always connect. You can always connect these things together. They're always connectable. So this is real code, this is actual test, where this is what it looks like. And this is actually very similar to the previous talk, right? So at the top of this function, we create an organization. We say, well, we need a mobile device. We're going to give it the name installer. We're going to submit that installer's cryptographic material to the backend, their public key. We're going to endorse a role because installers are able to actually put these hardware devices into the vehicle and register it as part of the organization. We have that installer go ahead and create that vehicle. Then we have a mobile device that's a dealer, and we make a mobile device that's a customer. Again, we submit their public keys. And then finally, we say that the dealer is allowed to transfer ownership of vehicles. Now, the thing about this, you can read it, even if you don't know Lisp, this is what the customer talks about. This is in the domain of the customer, right? This is how they talk about the problem. They have an app. I tried to enroll a thing. Didn't work. This test looks exactly like the business domain logic, and it's reusable, and it's functional, right? So it makes a state, and we just thread the state through the first argument, and at the end, we get this toy world state back. So we have functional scenarios. So now we write scenarios, again, close to the business language. The SMT and datomic functional storage is pretty nice. Something that's not obvious from looking in that previous thing is that we can go back to any step. We can go back to any step in time. We can run queries between, because everything is functional, between any two databases in a step. We have what are called state checks. We go back through the thing and we say, is this transition correct? Inside. We can take that because, again, since we used a completely functional thing, doing this sort of like history-based stuff, it's trivial. Significant improvement over our previous unit tests. We used to have lots of ad hoc unit tests. For complex scenarios, we never had to worry about the clients. We don't have to test with that. We don't need to boot Docker. It's just a closure program. We can just write tests in the REPL. It's really fast. So whenever we get a customer bug report, generally we just ask them to describe what they did, and we could put together a very nice, complete scenario of what's been described in 15 to 30 minutes. And it was generally a very good predictor. So we would often get bug reports, like typical, you get a bug report, customer says, this didn't work. And we like whip up a scenario, takes us about 15, 30 minutes, and we say, but it does work, so actually we can assign the blame now much to something else. Maybe it's in the SDK, or actually, more often than not, the customer forgot to mention something and they were doing something strange, right? But this is huge. Like the business value of being able to, within 15 to 30 minutes, say, yes, we verified that that could be the case or not, without having to boot anything, right? Just writing a test. That test is enough to tell us with confidence where the bug might be. Was big. Okay, so we have a Lego block. This idea of taking a world state and returning a world state. Again, the textbook functional programming thing. We use that, again, to provide a lot of both value to ourselves and to the customer. So once you have this Lego block style model, then the next thing is you might want to generate instructions, because the problem with unit tests that people write is that, I made one dealer, I made one installer, I made one customer, I made one vehicle, and I did a couple things. But the real world doesn't look like that. In the real world, there are many operations happening. But nobody wants to write that unit test because it's unreadable, right? The unit test in which things happen like they do in the real world, where there are many user interactions, it's a terrible thing to read. Nobody wants to read that, but we do want to test it. We do want to test it. That's why we started looking at property-based testing. If you're going to do this, the hard thing is just picking the right level of granularity. For us, we decided that we only needed a few things, and we really want to avoid fuzzing, because we already had, again, these unit tests with one user, two users, one vehicle, one dealer. We didn't want to do those. We really wanted something that was going to, be more like many users, many vehicles, many dealers. Test something we weren't already testing. So managing the search space is important, and we had a little trick. So we actually went and read about stateful property-based testing. And people are doing simulated annealing and custom search algorithms. And I was like, we're not doing any of that. We don't have time for that. We need to deploy this fix within 4 weeks. We can't do computer science research to solve this problem. We're going to figure out how to make a toy version of the search thing. And we'll get into that in a second. So the commands that we are interested in our particular case, were dealers can sell a vehicle to a customer. Vehicle operators can share keys. If you're a dealer, you can share a key. If you're a customer, you can share a key. Vehicle operators can revoke keys they've shared. And sysadmins can enable a bug fix and a feature, like I described earlier. It's a little bit small, but this is what it looks like. I mean, again, this looks like a toy, but these commands all line up. They all make sense. We have here, if you look at the third command it says, dealer 2 transfers vehicle 18 to customer 3. About 10, 12 steps later, customer 3 shares a key with customer 6, and about 6, 7 steps later, customer 3 revokes that key share, right? But this is awesome, right? Even though this language is so simplistic, doing this creates hundreds of database transactions. And these things get decomposed into many, many, many operations, right? Many, many operations occur from what is a trivial series of commands. And again, prior to this, we had no test of this level of complexity, right, at all. So the big trick, the cool trick that we were able to pull to avoid the search problem, if you're used to if you know about property-based testing and managing search when you're trying to do something stateful, what we realize is that we already wrote these scenarios, and the scenarios have everything in them because we took this step. We put everything into the toy state. Everything we need to know about what commands to generate is already there. And in fact, what we did is we built a scenario with, I think, 10 dealers, 20 customers, and like 50 vehicles. And what's great about this is we don't need to deal with this beginning of the world thing. We have an initial world, and we tell the command generator, make decisions, choose commands based off of this already non-trivial world. And we don't have the search problem. We're not floundering making uninteresting scenarios. We immediately make good scenarios. We jumpstart the generative test, and we didn't need to read any papers or algorithms to do this, right? We just have a good initial state. The commands are, by nature, because they're derived from a good initial state, they're good. For those who are curious, we use TestCheck. TestCheck is an open source closure implementation of QuickCheck with shrinking, but these libraries are available in any language. You could do everything I've described here with JavaScript. The stateful generator, also, there's nothing special about this. We wrote it in like 130 lines of code, right? As long as the property-based testing thing you're using has shrinking, it should be possible to write this in 100 lines of code in whatever your language you want to do it in. The evaluator's not that interesting. It's pretty trivial, right? We have these commands, but because everything is in the world state, each entity of interest has a name. The evaluator, all it has to do is says, okay, you want to share a key? Let me look at that name in the world. Okay, I know what the arguments are. Let's line them up. Okay, run it. So the evaluators, I don't even need to show a slide because it doesn't do anything interesting. Once you have the evaluator, then you can run the commands. And because the final value is this toy world state, you can look at it and be, okay, what is the hash? What is the SMT hash now? We also, in our test, we capture all, like each one of these things eventually gets turned into what looks like the blockchain transaction. We record those, it's an encoded thing. And what we do to verify that the hash is reproducible, we don't play back the commands again. We take the recorded transactions and we play those back against a fresh state, and do we end at the same app hash? Other neat things that are important that this let us do is we could create a gold file. So we committed to our source tree a bunch of randomly generated commands and the final hashes. And then every time we commit to the source code, the original file has to pass. All those app hashes have to be the same as they were before. They can never be, a different one can never be produced. And so as we build out models, we make more of these gold files saying, these are hashes that can never change for all time. And it's checked in CI. And then finally, the last thing we'll show is everything I talked about, this has been a long journey, ended up with less than 10 lines of code. This was the final thing. So here we make a scenario which has, like I said, some number of dealers, 20 customers, 50 vehicles. I take the base scenario and I derive the initial state that I feed to the command generator, which is right there in the middle. Given that model, the model only has 4 commands, like the ones I showed with the addition of enabling a feature, disabling. It says, give me commands, 20 to 30 commands that are random, that make sense for that initial scenario. We run the commands, and then we get a final world state. And then we take the transactions, we have a clean state, we run those transactions, state 1 and state 2, and then we look at the SMT and we say, does the app hash match? So I finished this work about 4 months ago, and for various reasons it took a long time because doing the real tests was really hard. Booting up a cluster, checking it, all this stuff, but I was able to write this test and I said, I think this code is ready. I've built an entire simulation of what I think will occur. It's pretty good. I think the prediction's pretty good. I don't know, you'll have to tell me though. And so DevOps, they set up a cluster, they took the production transactions, they ran them, 3 nodes, they went ahead and toggled the feature, they made more transactions, then they brought up a new node, and did that node reach the same app hash as the others? Yes, it did, right? So I used, again, textbook functional programming, no type theory, right? This is just really, this is stuff you've seen at every conference. And I needed this to prove that we could upgrade and downgrade the production system and not, break everything. So takeaways. Creating toy models allows us to create better unit tests. So I mean, you don't have to do the whole thing. Hopefully there's takeaways from this talk, regardless of what you're doing. Creating the toy model allowed us to write better unit tests, right? This whole act of doing the simulation allowed us to reason about the software much faster. I mean, I would say, 10 times faster, right? Before we were using the apps and trying to figure out what was going on, just creating the whole toy world thing already made our unit tests way better, our time to respond to issues from the customer way faster. And also, they were much easier to read, right? Actually doing this step of creating the simulation made tests easier to understand because, again, it's in the language of the domain. The stateful property-based testing stuff, was necessary to increase our confidence that if we make code changes, that it would work. Because in our work, backwards compatibility is a hard requirement because of the nature of the blockchain. So hopefully this was interesting, and hopefully you see that actually, I found these diagrams on Google. It's like, one diagram says 67% of your time as a software developer is maintenance. This other one says at least 30% of your time, right? But not that much time is doing new things. Most of your time is spent doing, maintaining this stuff or testing this stuff. And I think hopefully this talk is a bit inspiring that we can be much more creative and playful we can be very serious. Yes, the end result is very serious, but by thinking differently about what may look like, I could never use that. It's too simple. It's too simple. Hopefully this talk gives you inspiration for that actually increasing the software quality can benefit from very, very simple ideas, and actually it can be a lot of fun. I mean, I can definitely say with a fact, our entire team, after the testing thing, everybody was like, oh my God, I can read the tests now. They make sense. They're exactly what we're doing, right? This is what we're doing. So I think a lot of you shouldn't look at software maintenance as a bad thing. I think there's a lot of room for innovation, and hopefully this talk gave you some ideas. Yeah, thanks.
Thank you, David. That was great. I have a personal takeaway to share. I think it's difficult sometimes to pursue property-based testing, at the application sort of level, right? At a systems level, and so we often pick sort of small-scale examples, sometimes significant ones, but still relatively small scale. And so I guess the takeaway is, if you do everything functionally, everything is a data structure, then maybe we can pursue property-based testing at that kind of scale too. Yeah, so we have a question on, is it AirMeet? I forgot the name of the app. Okay.
Oh.
So I can read that out. What is the difference between property-based testing and stateful property-based testing?
So normally, when you build a generator, it doesn't depend on a previous value. So when you're doing stateful property-based testing, you're having the generator produce a sequence, but you make a generator. It's like the generator is a list of numbers. Well, the next number doesn't depend on the previous number. Unless you code the generator right, the next number does not depend on the previous number. And it's actually a bit of work to make a generator that produces a list in which each value depends on the previous value, or might depend on the previous value. So that's what stateful PBT is. You're using a generator in which the sequence depends on something that happened before. Hopefully that answers the question.
Okay, is that a second question? Yes, it is. Okay. So how relevant are academic contributions, papers published in scientific journals, to your work?
Good question. So, I hope I demonstrated that at least for the Lego block idea, functions that take a world and return a world, you can open up any intro to functional programming. You can go watch talks at conference and you think you would never use it. That's my point, is that it is usable. It's trivial, but it's still useful. The stuff about the domain language, I mean, that was just a decision. I'm like, we don't need fancy features to make a toy language. This is all that I want. It doesn't need to be more complicated than that. That's just taste. Other people might have tried to make it more complicated. In fact, this is the second time internally that we tried to use property-based testing. And the first thing, because we didn't have so many ideas and we didn't try to make it super simple, tried to do too much. And it was really hard to understand. So that's my advice. If you're going to do this, the command language should be as simple as possible, and you should not have very many commands. You should think about what you're actually trying to test. In my case, it was feature enablement, disablement, and I focused on that, and that language had to be simple. This is not going to be in a book, right? This is what we discovered. That's just practical industrial experience. Property-based testing, we did look at some papers because, we saw that search was a problem, and of course, we hadn't come to this idea about the initial state, so we did read a bunch of things, but everything was kind of complicated, everything was hard to understand, there weren't sources, and we sat back and said, well, do we need any of this stuff at all? Well, we don't actually want to start from a zero state world. We don't want to start from an empty state. It's not important for the thing that we're trying to prove. Wow, we could just derive. We already have unit tests, we can derive the initial state, just feed that to the generator, search problem is gone. So again, we read the papers to just come back and come up with a more practical solution.
Okay, so I guess it's time for in-person questions.
Thank you for the talk. So I have a question regarding the mismatch between the model and the production code. Do you see that there's a possibility that over time you would add some quirks in the production code, but the model start to deviate from it? How would you foresee that, and how would you solve it?
There are, of course, small deviations, but they don't really affect the predictive power for the thing that we're testing, right? That's the important thing, right? Like, yes, there's deviations, there's things that are small, but not about the things that we care about, right? So there may be things about the nature of mobile devices or the SDK that we actually build that are slightly different, but that hasn't really come up because for the property-based testing stuff, we're looking for global properties of the system. We're not testing the nature of individual actions, and if there are tiny differences there, it doesn't matter. I mean, if you think, it's like physics, right? The little things for the thing that you're actually looking for, those little differences don't matter as long as this big thing you're looking for is agreed upon. It may be the case, as you say, that we need to correct for that, but honestly, that's often done with simpler unit tests. We have simpler unit tests that check these sorts of things. I would say, to a large degree, it just hasn't been an issue. It hasn't been an issue. It's mostly been a benefit. But I agree, yes, it has happened. We've had to correct a few things, but it hasn't been a burden.
Okay, another question at the front.
Thanks for a great talk. You're probably aware of this system called TLA Plus for modeling distributed systems. I'm wondering if it would be applicable to your problem, and if yes, why didn't you choose to use it?
It probably is, though in this case, this is not a distributed systems thing that we were checking for. It was checking for whether the code allowed upgrades and downgrades, right? It's not checking like the properties of a distributed system. I know TLA Plus is great at that. I'm aware that it's used for that. I'm sure there are areas in which, in our software, where that type of modeling would benefit. We're not against it. In this case, we really, though, needed a simulation, a thing that we could run. Also, the issue with more sophisticated tools, I would say, is that we're a closure team, right? So there's a benefit. Yeah, it's not like super fancy, it's not super mathematical what we've done, but actually, people can understand it. In fact, before I got on the plane, we had a developer who I think has only been doing closure for like 6 months. He implemented the second generative model. So he took the work that I'd shown and he made a new model. And that was feasible. And I definitely think that there's advantages, like yes, other modeling tools are important, But sometimes you see, we can make a model, it's in our language that we're all comfortable with, and it's easy for the team to understand. And that's primarily why we went that direction.
Whose question's next? If you raise your hands, we have to like raise them reasonably high and keep them up because, thanks. I mean, that's the same height, right?
Thank you for a great talk. So I wanted to re-ask and to clear something. So you are basically taking two versions of your code, so the version without the changes and the version with changes, and you simulate you simulate your customers and you simulate your production with this toy, and then with in time of this simulation you compute the hashes of this tree, and so that's how you prove that two versions produce the same behavior? Or am I correct? Or?
I mean, proof is, you know, when I say prove, it's, come on, it's like, nobody wrote any math for this, right? But because it's run on every commit, because the command sequences are quite large, because the testing coverage is quite large, because it's really testing, like, even though I say share key, it's super complicated. It's like a person saying, I want to endorse this person. That person has to respond. This person has to confirm. It requires many steps. The test coverage is massive if there's 20 commands. And it's random every time, right? So it's not like it's a proof, but we've been running these tests for 4 months and we haven't seen anything. And the test actually does the upgrade downgrade. So it upgrades the code, that stuff, the new code works, downgrades the code, back to the old behavior. So not a proof, but it's like physics. Observation is telling us consistently that it's working.
Okay, next question. Great.
Yeah, hi, thanks for the talk. I wonder about the command generation. How do you ensure that the sequence generated makes sense and at the same time don't limit the variety or like the scenarios that you end up generating?
It's a very good question. I mean, I could have talked 50 minutes about that, right? It could have been a 50-minute talk just how to build a model of that's interesting. And actually, so it took us, I don't know, probably took about us a week and a half. So what would happen, to your point, we had commands, the commands looked okay, but the moment we tried to evaluate them, like for example, we did a thing and we said, oh, this is great, let's run it. And then there's an error. And it's like, wait, what happened? And it's like, oh, it shared every key that you could possibly share. There are no vehicles left to share, and yet it tried to generate a share command. So there was a constraint that was missing in the generator to check, is there anything left to share, right? So that took time. We had to like run it, see that, is that a bug? Oh my God, did we find a bug? No. Our model is bad. So it took a while to make sure that the model made sense, that all these constraints were present. It's not easy. It's actually really fun. We had a lot of fun. We learned a lot. Actually, there were constraints in the domain that we never thought about because we never had to write them down. And definitely making the model, it's actually, you know, a really great way to really understand some implicit things.
Right. We have an online question, so I'm going to read that out. Why didn't you choose to also create your own version of test.check?
Well, I mean, in general, I think this talk was that we didn't create anything of our own. We came up with no new ideas. We didn't make anything on our own. Why should we do work? Why does anybody want to do work that they don't have to do? I do not understand, right? It's like, if I don't have to do anything, sign me up. I mean, that's better. There was no reason to write our own version of test check. It's already been written. Why? I don't need to do that. I'd rather work on the problem.
Okay, more in-person questions.
Thanks for the talk. I want to ask about the process when a new feature is introduced. Do I get it right that now you have to write the function for the feature, the function for the new, for the model with the state at the beginning and also a new command, I guess, for the command generation? Is that roughly the process of like what needs to happen in the various places of the
So it
base?
really depends. I mean, the cool thing about this system is that we now have a generic library of commands. So when you write a command, anybody can make a model. See, the model is make a command and the generation for the arguments of that command. And that is an independent task, just making a particular command and making sure the arguments are correct. You could do that in isolation. Your model is choosing which commands are going to be tested. And we can make as many, we can combine them in any way we want, right? Somebody might do something that requires no new commands, but it requires a feature. That doesn't require any work, right? They just implement a feature, they go and put it in the source code, the tests are going to run, they're going to verify that it's not broken. Already be covered. If somebody makes a true new piece of functionality in the back end, yes, there is some work to do. We have to set up this toy state thing around it, then we have to go make a command for it, and then we have to make a model that uses it, and then we are confident that that works. But you're right, but I'm just pointing out that in some cases, a little bit of work, some cases, more work.
Let me just quickly check David is okay with more questions. Yeah?
Sure.
Okay.
I mean, as long as I'm willing to answer questions, as long as you have questions.
Right. I'm not sure I'm okay with all this running.
Okay, so again, thanks for the talk. I wanted to ask you a question about the debuggability of this, because you get the result that state X is not equal to state Y, and that's fine, I guess. But how about actually going step by step in those scenarios and actually finding out where the problem lies?
So it's a really good question. It is a good question, but let's remember, when you say you're comparing the thing, you cannot forge anything in the SMT. It's impossible. You cannot forge anything in the SMT. You can do all these kinds of writes. You're always going to get one cryptographic hash. So when I'm checking that cryptographic hash, I am checking hundreds of transactions. You just can't get to that value by any other means. So it's not a simple test. It looks simple. It looks like a toy, but it's very powerful what it's saying. It is saying that all the authoritative documents are exactly the same as the other run, right? And we're actually writing those to disk, and we're actually checking all the hashes all the way up. So it's a very strong property check. It is not a weak property check. There are, of course, but still to your point, valid criticism. But this is what I was trying to say about because we used functional programming, and actually we can reify the history of each step, we actually have state-based checks that can run backwards through time and actually check each transition. We have assertions like that. You can combine, there's nothing about what I've said that is one or the other way. All these things can be composed. We can reuse the unit test scenarios, we can add checks across all the straight transitions, and still run the property-based, what looks like a simple check.
All right, more in-person questions? Someone's pointing somewhere, but I'm not sure.
It's always got to be somebody in the back.
All right, okay. I was trying to scan the room systematically, but it wasn't working. Where did we go? I'll go around.
Sorry for the running, and thank you for the food for thought. Both in the past and through your talk, I've noticed a lot of parallels between blockchain and the work you're doing and the sort of event sourcing pattern. I wonder if there's any conscious cross-seeding of ideas, and then sort of maybe as a secondary, like, is event sourcing a potential toy blockchain?
I'd have to think about that. I mean, I followed the event sourcing thing. There are things that I would say, I don't know. I haven't been following event sourcing that much. The thing that I never liked about event sourcing, if I was going to say, is that like there's a lot of manual work. I mean, maybe there are like really good turnkey solutions now for event sourcing. I haven't looked at that. Does anybody want to say? Does somebody know of something like turnkey event sourcing? Does that even exist? Yeah. See. So whenever people give these talks, this is the curmudgeonly David Nolen like. Yeah, it sounds like too much work. I'm not going to do that, right? And it's actually why we use Datomic. So Datomic does a thing which I think is just better. I mean, it's just better, right? Because it's not a log, it's not event sourcing, there's no snapshots. It's just a real, immutable, persistent data structure on disk. All the things you like about SQL are present. You can say, I want to go back to yesterday's database, and it takes milliseconds. And I want to run a query on yesterday's database. And it just solves that problem that people want. The typical problem that I see people want to do with event sourcing, we just chose Datomic because it solves that problem. It may be in the future we can't use it, but my experience with Datomic, because it's related to the types of things we'd want to do with event sourcing, is that it requires us to do less work. We stay focused on the actual problem. That said, I think event sourcing is cool if that's the only route and it's not practical to adopt a closed source database. And I definitely think that there are probably things that I've said that could be applied to people who have built an event sourced architecture and want to validate something.
Okay, so I'm just carefully taking a look. Anyone for another in-person question? I think we're done. Oh, there's one.
Okay, this will be the last one. Last question.
Yeah, thanks a lot. Very inspiring talk, actually. A lot to think about, even in product I work at. I wanted to ask, have you thought about problem of accumulating garbage code that is not being executed? Because during the talk you mentioned that you cannot remove code because of the blockchain thing. How can you remove the code in such situation?
Well, so that idea, again, I presented many things. It's the purpose of the gold files, right? These historical hashes that were computed in the past that should always be computed, right? The same way in the future. So it's possible that we could produce more of these, we could have more coverage. Like, just as anything, coverage is a problem, right? So I showed how we solved a particular thing, but we need more coverage. But if we had more scenarios where we know what the hash should be and that they should always be that hash, then we could delete code. And as long as all those files still compute to the same hash, it's probably okay. But coverage is extremely important. Therefore, we don't want to just do it. But maybe at a time when we are confident after a year with this approach to developing on the chain, we feel really good about it and we feel like we have enough historical information and those are being computed the same way, then we can start looking at, is this truly dead code, or can this be refactored to remove the things that don't matter anymore? Like, yes, we want to do this. It's not like we want dead code to sit around, but I definitely think for us, getting to the level of desired coverage is necessary first.
Okay, so lots of takeaways. I can't wait to think through them. How about a sort of final thank you to David?